Yeah, so I work at Argonne, and my background is applied math. I love machine learning and helping scientists apply machine learning to their problems. And yeah, the newer part of my research is the supercomputing part. But I work at the Argonne Leadership Computing Facility in the data science group. And I know tomorrow you're going to have a whole day on machine learning. So I hope tonight I can give you like a high level view of machine learning and how it might help your science, get you excited for tomorrow, and maybe give you some research ideas. So you could think of science as having several paradigms, like experimental, theoretical, computational, and data intensive. Although these are definitely not mutually exclusive, I know a lot of us do science that overlaps several of these paradigms. And the data intensive science is growing. As we all know, we have growing amounts of data, we have better computers, and we have ever improving methods. So more specifically, what is machine learning and how do you use it for science? There's these confusing terms. Oh, the colors didn't work out well for that middle circle. Looks better on my screen. So roughly, you can think of machine learning as a topic within artificial intelligence, and that's the term I'm going to use tonight. And deep learning as a method within machine learning. And a lot of tomorrow on the machine learning day, most of it will be deep learning, and that's because we're at the big scales, we're seeing mostly people are using deep learning, but not exclusively. So what is machine learning? It's a little hard to define, but one would be the field of study that gives computers the ability to learn without being explicitly programmed. So a classic example, that's a real example, is the post office wants to sort your mail by zip code automatically. So they want to be able to read your handwriting. And you can think of it as being a bunch of little images of each digit, and you want to label each digit as the digit 0 through 9. And if explicit programming could be you came up with a bunch of if-then statements for how to classify this, like if 80% of the black pixels are in the middle of the image, then label it a 1. Something like that, you have to come up with a bunch of rules. So in contrast to learning with explicit programming, in machine learning, we want to just see a bunch of pairs of the images and their labels and learn some function to map them. So as I'm sure you're all familiar, you can represent an image as like a matrix of numbers. In this case, it's all black and white, so each pixel, it could be 0 to 1 for white to black. And then we could plug that into some function, which I have drawn as a black box. And we want some function that will take in these images and output the correct label. And so in machine learning, we would have lots of image label pairs, and we want to learn some function to map it. And there's different kinds of tasks within machine learning. So just to briefly cover the most common ones, one is classification. So each data point has some category label, and you want to learn to categorize your data. So an example would be learning to tag Facebook photos with the right name after Facebook saw a lot of examples. So you input a picture of me, and Facebook knows it's Bethany Lusch. And more of a STEM example would be that you can label an X-ray image with a diagnosis after seeing lots of X-ray images that are labeled with diagnoses by experts. And this is in contrast to regression, which is a bit of an overloaded term, but in the context of machine learning, regression often means the task is to predict a numeric label, not a category. So predict like a real number. So that could be predicting stock prices after seeing a lot of historic data, Or a science example could be learning to predict the melting point of a molecule after you see a lot of experimental data. And this is a real example from Argonne. And another task in machine learning is clustering. So here you have an unlabeled data set. You don't have them labeled in different categories, and you want to just find groups. Maybe you don't even know how many groups there are. So this could be finding communities on Twitter, but this could also be finding subtypes of breast cancer. And tomorrow morning you'll learn about one method for clustering. And another approach or task within machine learning is reinforcement learning. So you have some agent exploring an environment, and it has some delayed reward. It's trying to learn how to get rewarded. And a classic example would be learning to play video games. So there's all these papers, things like learning to play Frogger by playing the game. And the delayed feedback is that eventually you get a score in your Frogger game. But in science, this could be something like learning to suggest useful chemical reactions. Now, I mentioned that deep learning is an approach within machine learning. So I'm going to say the fastest description of deep learning. I'm going to say one slide, and then you'll learn more tomorrow. Okay, so in deep learning, you have an input x and an output y. And in between you have some function. But it's not any form, it's the form of a neural network. And it's often drawn like this, which is why it's called a neural network. And in this drawing, each of these layers is that you multiply by a matrix, so I call them A1, A2, A3. Also, you add a vector and you apply a nonlinear function so that the whole thing is nonlinear. And you could have more layers. You could keep iteratively stacking that we're going to multiply by a matrix, add a vector, apply a nonlinearity. And there's some error or loss function to minimize so that you're fitting your data. And loosely, if there's a lot of layers, you call it deep learning. Or maybe just call all your neural networks deep learning. And you'll learn more about this tomorrow, but in order to fit your neural network with your data, you have an algorithm to iteratively improve the fit, and that means changing those matrices and vectors so that your error is lower. And I just want to say a little bit about deep learning to give context for the rest of the things I'm going to say. But we're at ATPESC, so we want to talk about big deep learning in parallel. So the first thing is you might have noticed that was a lot of linear algebra. Like fundamentally, deep learning is doing a lot of matrix multiplication and adding vectors. So it's fast on GPUs. So the data science group, we're excited about this whole moving to having GPUs on supercomputers. It's great for us. Another way that deep learning can be parallel is there's like a lot of detail in that deep learning, like how many layers you have, and you'll learn tomorrow there's all these things that we call hyperparameters, tweaking how you train your neural network, and there's not a lot of theory yet about how you tweak those. And so the embarrassingly parallel approach is you can train a lot of neural networks in parallel. Now, you'll also talk about data parallelism, which is like the common way to scale up deep learning. And that is that you have too much data to fit on one rank. Let's say, to be concrete, too much data to fit on one GPU. And so you put some examples on each GPU. And then based on the local examples on your GPU, you estimate how to improve the fit of your neural network. Then you communicate with an averaging across all the ranks, and you update the model. So this is like something that we do all the time, and you'll learn about tomorrow. Relatively well studied. The harder versions to parallelize deep learning are if your model doesn't fit on the GPU. And so then you have to communicate more often. So something like maybe some of your layers on one GPU, and then you need to move to another GPU to apply the next layers. Or the special case that is relevant for things like fluid dynamics, which is that each example is really big, because let's say it's like a whole mesh, and the example doesn't even fit on the GPU. And so maybe you want to split your examples spatially across different GPUs along the lines of a domain decomposition. And so these are the kinds of things we have to think about as we go bigger and bigger with deep learning, but they're a lot harder, more like open research questions. And just if you're wondering what the software is like, in deep learning, it's common to use the Python packages TensorFlow and PyTorch, and you might say, oh no, why would you do Python on a supercomputer? But we have fast backends, so it's really just the Python API, and so you can use the right version of Python that's compiled to have the appropriate backend for your supercomputer. Then we add on other Python packages like Horovod and DeepSpeed for distributed training, and for quote-unquote classical machine learning, meaning not deep learning, there's other things like the Python package scikit-learn if you want to make it fast on your hardware. If it's like NVIDIA, you might use their Rapids library. If it's Intel, there's a $1 backend for scikit-learn and so forth. So the big idea here is you get to use Python with a lot of high-level functionality, and it's portable because there's not a lot of differences to move to different hardware, because you've got these fast backends. Okay, so why should you care about machine learning? Machine learning is doing some cool things in science, and I'm going to start with a couple examples that I'm not personally working on, but are cool. The first is cancer research. So that you might have heard of the CANDLE project. It's part of the exascale computing project, and it's one of the earliest science projects for Aurora, meaning they were chosen to get early access to Aurora and prepare for when it comes. And they have several science goals. One is predict drug responses. One is to understand the molecular basis for a particular pathway that's relevant to cancer. One is to develop treatment strategies. And for each of those, we can look at how is machine learning helping and how is supercomputing helping. So machine learning is helping in the drug response problem because it can learn these like complex nonlinear relationships between drugs and tumors. So you have a lot of data on drugs and tumors, and you want to learn some weird nonlinear relationship. For the RAS pathway problem, they're using machine learning to guide molecular dynamics simulations. And for the treatment strategy problem, they're looking at clinical reports and how to like read and encode it. And why do you need supercomputing? Well, one thing they're looking at is being able to run those molecular dynamics simulations and the machine learning on the same platform. So the machine learning can guide the simulations. And of course, they easily have tons of data. Also, they look at things like either having an ensemble of many machine learning models or having just like really big machine learning models. And so I put a link to their project if you want to learn more. And another example is from neuroscience, which is a connectomics project that's also getting ready for Aurora. And the goal here is that you want to make a map of neurons and their connections, and what you have is brain images. So for example, you have a mouse brain that was sliced and then imaged, and you want to stack that back up and segment in 3D. So here's a little picture of what it looks like in 2D and then what you want to happen in 3D. And there's a lot going on here, but a machine learning contribution is accurately segmenting out those neurons in each layer and following them through the layers instead of having a human annotate it all the time. And the supercomputing is I like this example because the supercomputing makes a lot of sense, that right now they can do more like a millimeter cubed, and as you move to bigger supercomputers, they want to move to things like a centimeter cubed. And they're moving towards being able to handle a mouse brain, which is something like a centimeter cubed at the 10 nanometer scale. And so it makes intuitive sense that the bigger the supercomputer, the bigger section of a brain they could do this for. Another project, this one I'm involved in, is Lattice Quantum Chromodynamics, or Lattice QCD. It's a machine learning project for Lattice QCD. It's getting ready for Aurora. And the science goal is to do calculations of interactions between different particles that could be dark matter and nuclei, which would then inform experimental searches. And this would be doing calculations that are currently intractable. And so one way to make it more tractable is they're using a machine learning model to improve the sampling. And they need to sample some target probability distribution. Conventional methods get stuck in one region, and the machine learning methods are helping them explore the probability distribution better. And this gets harder as you do like a finer spacing in their lattice. And then the supercomputing is needed. Well, Lattice QCD in general is done on supercomputers, but even with the machine learning, you still need supercomputers. And as you scale to finer lattices, you need like enormous amounts of memory. And as you they're gradually incorporating the more complete physics. So this is a case of like coupling AI and simulations and speeding up the calculations that are currently intractable. And just to mention a few of the other machine learning projects that are getting ready for Aurora. One is predicting and mitigating disruptions in fusion, and one is discovering singlet fission materials for efficient solar cells, and another is looking at scaling fluid dynamics simulations. So I wanted to give you an idea of the broad ways that machine learning is being used in science on supercomputers, but now I'll talk a little bit more about things I'm more specifically working on. And lately I've been working on ways to combine simulations and machine learning. And for example, this can mean training a surrogate model. And by a surrogate model here I mean some simpler mapping from inputs to outputs that would mimic something more complicated like a simulation. And you might hear this called an emulator. And we're using machine learning to fit a surrogate to our training data. And surrogate models could be useful because simulations, as you all know, can be very computationally expensive, and the surrogate could be orders of magnitude faster. So I'm going to show some examples of how much faster we can be. And of course, there are downsides to not running your simulation. So you could compromise by just replacing an expensive part of your simulation with a surrogate, or an inaccurate part of your simulation with a surrogate. And this can enable things like exploring parameter space. So if you can run, instead of running a very slow simulation, run your surrogate really fast, then you could explore some parameters, get an idea of good parameters, and then run the full simulation in an area that you tentatively think is good. Similarly, you're trying to design something, and you could evaluate searching that design space with your surrogate model. You get a tentative idea of what seems to be good, then you run the full simulation. You can also assimilate data, like from observational data, faster to a surrogate model than a full simulation. And also sometimes you want to explore uncertain inputs, and if each simulation with a different input is very slow, then it can be infeasible to fully explore the effect of those uncertain inputs. So this could be sped up by using a surrogate model. You also might want to use a surrogate model to save some compressed version of your simulation that you can't save off to disk because of I/O limitations. So one example is we wanted to do a proof of concept of this for CFD. Specifically, we looked at simulating the flow past a backward-facing step. And for machine learning, we didn't replace the whole simulation. We just replaced one PDE that's involved in this simulation. The machine learning model predicts viscosity, and we feed that back into the simulation and solve the rest of the equations. So you're like keeping the rest of the physics. And the result in this proof of concept study, we had reasonable accuracy, but the solution was 5 to 7 times faster. And some challenges were, one is the literal software issue of how to communicate between your simulation code and your machine learning library. In this case, we were looking at OpenFOAM, which is a particular CFD solver, C++. And I mentioned before that machine learning is typically done in Python. So there's like really nice Python libraries for machine learning that make it really easy. But it's not trivial to have your C++ code and your Python talk to each other. In this paper, what we did was we used the C API of TensorFlow instead of the Python API, which was like non-trivial enough that we put up tutorial code, and I can point to that later if you're interested. For a follow-up paper, what we did is a little different angle. We had OpenFOAM call Python, and so that was like a non-trivial too, to just figure out from the C++ code to call Python, have the data come back, and we're further improving that on making sure we don't copy the data. Another challenge in this kind of problem is designing your machine learning problems so that you're able to do some generalization. So in this case, we wanted to generalize across the step height changing, so a little bit of the geometry changing, and the boundary condition changing. And so it's kind of like a limited exploration. And you can think about how to set up your machine learning model, what the appropriate inputs and outputs should be, so that you can generalize across the pieces you want to generalize across later. So if you're interested in that, it was published in Computers and Fluids, but if you don't have access to that, it's also on arXiv. Now, we went a little further than proof of concept to look at automotive engines. And this was a 2-year project at Argonne, with very interdisciplinary, with CFD experts and then people on the machine learning side, to look at speeding up simulations of automotive engines. And I'm not a CFD expert, but I'm told the most expensive part of this simulation is simulating what happens inside the injector. And so what we did was we learned a surrogate model for just what's happening inside the injector. And then you still run the rest of the simulation. And really, we didn't need to know everything that happens inside the injector. We just need to know what happens at the exit of the injector. So that would be like a boundary condition for the rest of the simulation. In the broader context is you want to be able to design an efficient engine, but you can't run tons of these simulations where you keep tweaking things. So like I mentioned before, you potentially could explore design space with your faster surrogate model, get a preliminary idea of what seems good, and then run the full simulation. So in this case, we predicted just like the 2D disk at the exit of the injector with machine learning. And then you feed that back into the rest of the simulation. And the surrogate for predicting what happens at the exit of the injector was 38 million times faster than actually running the simulation in the injector. And we did some exploration of propagating the uncertainty from that prediction into the rest of the simulation. And this was a whole sequence of papers, but I just put references to a couple of the more recent ones. And we also explored, since we did some uncertainty quantification, how that could help you choose which simulations to run next if you decide that your machine learning model isn't good enough and you want to run simulations, but you don't want to just run some random ones. And so this is the kind of thing where machine learning could enable something that was completely intractable before. Another thing I'm working on right now is accelerating weather prediction. And we want to move to climate models, but our initial paper was on the weather scale. And we were just predicting geopotential height. The machine learning was, you could think of it as replacing the numerical weather prediction, although we're just predicting one quantity. So you could think of it as a surrogate model. And numerical weather prediction would be a very expensive simulation. So the surrogate model is much faster. It's also differentiable, which is convenient for doing data assimilation. So you want to assimilate observational data in order to improve your numerical weather prediction. And here, our surrogate model was a neural network. And so we easily have the gradients of our neural network. And that makes the data assimilation faster. So we're able to do the data assimilation on the order of 1,000 times faster, both because the surrogate model is faster than the simulation and because we have these easy gradients to do the data assimilation. And this was a preliminary paper, but we want to be able to predict more quantities. And because of data assimilation being faster, be able to integrate more observational data than you normally could, and move to the climate scale instead of the weather scale. And at the climate scale, our vision would be not to replace the whole climate model, but just a piece of the climate model. And Piyush is here, he's working on this project with me. Any questions about those projects before I talk about some other things?
How you create this surrogate? Is it that you run the expensive one, different cases, and train in your own model and results, or is it more elaborate than that? But how do you create the surrogate?
So for the engine, what we had to do was run the expensive one something like 30 times, and then train it on that simulation data. For the weather prediction, the data is just around. For the backward-facing step, we also had to run it some number of times. I don't remember the number of times. So if you have to run it too many times, that could dwarf your gains, if that's what you're getting at.
Is there some way to know, say you run it 30 times, a feeling maybe you should run 40, and then just how do you push the space to sort of guess what parameters the surrogate training wants? Mm-hmm. Is there an art to that, or is there more of a math side to that? That baffles me.
No, that is definitely a good question. So, in the case of the engine simulation, since our final model was formulated as the input is design parameters, and then, so what we did was first we had a machine learning model that does dimensionality reduction, just to go from the full simulation down to something small. And the other piece goes from design parameters to that reduced space. And then you can do that, the decoding part to go back to full space. The nice thing about having the input of the machine learning model be design parameter space is that you can, we could like literally plot it and pick things that are spread out as our training data or like the initial simulations to run. And then you know that if you pick something outside of that region that you're extrapolating in the sense of that like literal input to the machine learning model. But also we did uncertainty quantification so that we could map that on design parameter space so we can see where in that region we're more or less confident. So you're kind of like far from your training data. Does that make sense?
Yeah. Cool.
But in other formulations, it's harder to know if you've strayed from.
How many degrees of freedom were in that design parameter space?
For this, we did 3. 3 design parameters. Yes, so yeah, a rule of thumb could be 10 each. I think that's why we did 30. Yeah. Yes.
For such a low design space, have you thought about using polynomial models because those could work well too for such a low design space? Neural network is not necessary for those kind of things.
So the polynomial model from the 3-dimensional design space.
Yes, like doing polynomial expansion of polynomial expansions and like just representing in terms of polynomial instead of nonlinear functions of neural networks.
Like to go from the design parameters to like our low-dimensional representation. What we ended up doing was Gaussian process there because it would have uncertainty quantification. But yeah, we didn't try polynomials.
I have a follow-up question. For Gaussian processes, were your outputs all independent or were they all correlated?
Since I didn't write the code myself, I'm not sure how we set it up. It makes sense that they'd be correlated.
That's an actual problem. It's not easy to coordinate. That's what I was curious. Thanks.
Yeah.
So, which part of the climate model are you targeting?
Radiation. That's the most expensive.
If anyone didn't hear his answer, he said radiation.
Sorry?
I was just repeating your answer in case people can't hear. But it's taking us a while to formulate it well and talk to the domain experts. Like here. Don't want to get it wrong.
What's your feature space on that problem?
For this climate problem,
Yeah.
I don't know if we should go into it.
Oh, it's secret?
I mean, we're still. It's a work in progress. We're looking at like different locations and time, and
Essentially different, like at different times of the day, at solar zenith angles in different locations. What's essentially causing uncertainty in surface fluxes. So in the presence of clouds especially, there are 2 modules in there, clear sky versus cloudy sky. So in terms of different types of clouds present, how can we improve the uncertainty in the surface flux quantification? Especially because that differs between location to location, topography and everything. So that kind of thing.
hopefully it'll work out well. Then we can show you an awesome paper. Okay.
For the runs acceleration, how do you define the time steps in the input and the output?
Oh, yes. For this one, we were predicting steady state, so we didn't have to do the time step.
Okay, you predict the state.
For the engine, we needed to predict overtime, and so we used time as an input to our model that's going so it's design parameters plus time. mapping to reduced space, which I'm still not very happy about. I think we could have done something a little better. It was a little rough. But a lot of my papers, what we've done is you do some dimensionality reduction and then predict forward in time in the reduced space with like a time series model.
So do you use MSTM?
Yes. You said you are reducing the dimensionality of the design parameters at the time.
Oh, sorry. The dimensionality of the simulation itself, like the flow field. So there's already only a few design parameters we were considering. Yeah.
For the engine calculations, did you reduce the number of chemical species?
This would be a question for my collaborators. I know we emulated like something like 5 flow fields, and I don't know what simplifying assumptions we did. Sorry about that. Yeah.
Your circuit model is 30 million times faster. Like, what was the comparison? Like, did you train multiple cases, or was it like a single engine? What was the design space?
Okay, after you train it, if you wanted to try a new design parameter combination, this would be comparing, like, input those into our surrogate model and get the emulated flow fields versus run the simulation.
Like how the distribution parameter, or how much extrapolation could do. You know, like 38 million times faster is a huge number.
Yeah.
So like how is this measured?
This is like after the training, so you have the upfront cost of the training. Now you want to do a new point design parameter space, and if you just plug it into our emulator, very fast. If you run the simulation, it takes much longer. So we're comparing those times, and then there's the caveat of you still run the rest of the simulation, because this is replacing the injector part is replacing the injector is 38 million times faster, and then you still run the rest of the simulation. So there's the upfront cost of we ran some simulations first, saved them, trained an emulator. Although this would be, since we only ran 30, this would be dwarfed if you plan to explore design parameter space more extensively. And then the extrapolation question would be like, you wouldn't want to go outside the box that we explored if you kind of mapped out those 3 design parameters. So I think one of them was like fuel viscosity. So I wouldn't want to try a value outside the range of what we tried before, because neural networks don't extrapolate well in the input space. At least this was a Gaussian process, so you'd quantify how far off you are. But does that make sense?
Just a follow-up question. Was it like you said you quantified uncertainty?
The mapping from design parameters to the reduced space was a Gaussian process in our final papers, but we used a neural network for the dimensionality reduction. So the part of the dimensionality reduction is harder to quantify uncertainty. We'd have to do some kind of Bayesian approach or something like that. Yeah. Okay. Okay, now a lot of these examples that I talked about involved coupling machine learning and simulations, and I kind of alluded to it. This is like a computer science and a software question. And so here's some diagrams that I find helpful to think about different ways to do this. And one is that they're loosely coupled. You have like the simulation and the AI could be running, let's say, on different processors. Like the simulation's running on some CPUs and the machine learning's running on some GPUs, and they're not blocking each other. Tightly coupled would be like they're blocking each other. For example, in our backward-facing step example, we need to call the machine learning and pass the answer back, so you're blocking the simulation. And then you could be very loosely coupled by having totally different resources, like you're coupling, you're running something on Cerebrus and you're running something on our supercomputer. So I wanted to wrap up with some open challenges. You could think of these as caveats, or you could think of them as opportunity for research. So in general, with machine learning, it's you have this problem that a lot of people have brought up, that you want to generalize well to other data. So if you trained on engine simulations with these certain design parameters, you want to know if you can then apply your model to other design parameters. And like I mentioned, at least with neural networks, extrapolating in the sense of like the things that you're putting into the network is, you just shouldn't do it. If you mean extrapolation in some other sense, then it might be okay. So you want to formulate your question carefully so that when you apply it later, you're interpolating, not extrapolating. Machine learning is often hard to interpret, and typically you're lacking in guarantees. And one way to build trust is that you build in uncertainty estimates, but that's like an extra level of work and open research. And now that machine learning is being applied more and more to science, there's increasing research in how to incorporate your domain knowledge. So like if you know that mass should be conserved, how do you bring that in? And one thing I love about deep learning is that your loss function is very flexible as long as you write it in terms of things in the library. They're all differentiable. You can be very creative. But this is definitely an open area of research. And it can be hard to troubleshoot machine learning. It can be hard to know, is the error high because you did something wrong, or is the error high because, is it a bug, or do you need to make your model bigger, or, yeah, hard to troubleshoot. So you need to formulate your problem carefully, and you have to be, as far as generalizing, you have to be very careful that you have a appropriate held out test data that you don't look at till the very end and is representative of how you want to use the model in the future. In the context of machine learning for simulations, then you have this, you might be extra challenged about having limited training data. In some other contexts of machine learning, you just have like ridiculous amounts of data. For simulations, when they're expensive, you might have very limited training data, especially compared to how high dimensional they are. And so then you have the question of how should you choose diverse simulations? Like if you're only going to run 30 of them, which 30 should you run? And the larger the simulation, maybe as far as high dimensional, maybe the easier it is to overfit unless you formulated it nicely. Then there's this question that I alluded to of if your examples don't fit on one GPU, that's a kind of parallelization that's less well studied. If you're working on something like CFD and your data is unstructured meshes, you have clear spatial patterns. When you do deep learning on images, convolutional layers are great, but there's no like straightforward way to apply it to an unstructured mesh. That's an open area of research. And time series models, which I think you'll learn about tomorrow, they often have a hard time with long-term stability. Like fine for 10 steps forward, problems if you go 1,000 steps forward. And then there's sort of these computer science questions if you're doing machine learning and simulations at the same time. Like keeping your resources busy. If you're passing data back and forth, do you have low overhead? I mentioned the software issues like communicating between C++ and Python. It'll slow you down if you have to write up some code to do that. If your simulations are too large to even ever save to disk and you want to do the machine learning at the same time, then you're not really in the typical machine learning case, especially with deep learning, it's typical to loop over your data over and over. But if your data is too big to save to disk, then maybe you only get one pass. That is like, now you're adding another level of complexity. And if you're deploying your machine learning inside a simulation, then there's questions of, do you accumulate too many errors as you keep iterating forward? Do you predict something non-physical and your simulation is confused? If your surrogate is just for part of the simulation, you're going to feed it back in. If you train it like offline, like you saved off inputs and outputs, and you don't have feedback from how these errors are going to propagate through the simulation, that could be non-ideal, but maybe it's not computationally feasible to train with the full end-to-end workflow in mind. So, in summary, I'm very excited about machine learning. It can enable approaching scientific problems that were out of reach before, but there's also a lot of open challenges, or maybe you can think of it as potential research topics. So, thank you. Ray, do we have time for more questions, or?
Depends on how much they want to do something else. Like either talk to the software people or play volleyball, as the case may be.
Yeah. Okay.
Let's say a few questions are fine.
Yes, Peter.
In your experience, how much data do you need to take full advantage of something that a large HPC cluster can offer you?
Oh, that's a hard question. I think part of what's hard is there's a difference between like each example being really big versus having a lot of examples. I think a lot of there's also a big jump between like you have a couple GPUs in your lab versus if we have 10,000 or something. I don't know. Do you have thoughts on that?
Oh, when it comes to data, more. Just more. As much as I have for storage. So.
So you discussed about how like including physics or equations could be interesting, and it's easy to do it in loss function. But I'm really curious about. I want to know your opinion about the practicality of it, because like I have tried things like including loss function and just not including loss function, and the accuracy doesn't change. So it seems like because the input-output mapping will still be quite similar by including the loss including the equation, the loss function, considering without. So I just want to know your opinion about the differences.
Yeah.
For forward problems, not for inverse. Inverse it really works, but for forward problems it makes less sense to me. I want to know your opinion about it.
So an example would be like we were looking at physics-informed neural networks.
Exactly.
Okay. So for those who don't know, physics-informed neural networks is like a formal term, PINs, where you can, let's say you know a PDE, you can put it in the loss function, and you say your data has to follow the PDE. Although it's just a penalty in your loss function, so you're not. It's not like a hard constraint, so you're kind of encouraging your data to follow the PDE. I haven't done much of it myself, so I've heard it can be great, but it can also just not work. So and it means that you have to already know your equation. Your equation has to be accurate. I think it's interesting when people do hybrid. Like there's some papers where your equation's pretty good, but you use the machine learning to learn what's wrong about the equation. I think that's cool. But I've heard people say similar things to you, that it just didn't really help to include the equation.
Thanks.
Yes.
You had mentioned emphasizing to make sure you're exploring the interpolation, like the parameter space, interpolated parameter space rather than the extrapolated one.
Yes.
And I'm thinking that's the same way into like maybe something that I kind of like say that like ensuring you're maintaining like stationarity of the probability space that you're working in. And I'm thinking like how do you kind of like manage that kind of like ensuring stationarity? I'm thinking the application of like climate weather models where you often use like kind of very complex dynamical systems that perhaps even under climate change or dynamics changing, and thus then are not stationary. Like how do you contend with that, and say some of the like models you're training, and maybe the amount of time needed to retrain a model to explore different spaces.
I think that's a super important question, especially with climate, because if we just train the model on historical data, it might not work for the predicting the future. I don't think there's a easy answer. I know in general machine learning, one term for this is data set drift. So you trained your model, you deployed it, like Google deploys their model or something, and the data set changes over time, like the distribution drifted. And I don't know a lot about the methods for that, but it's definitely something that people are at least working on. Like, we need to monitor it and then adjust. And I wish I knew more about what they're doing, like in actual industry, to handle this. I think to some extent, if you can anticipate the direction that you might want to explore. So an example is I was working with someone in chemistry, and their training data was all elements of a certain part of the periodic table. And then he wanted to apply it to elements later in the periodic table, but an input was like molecular weight or something. And I was like, no, that's definitely going to be extrapolation. So sometimes you can anticipate this and say, you planned to deploy your model on inputs that are bigger, and so you should include that in your training data. And I think you can't always anticipate. I think that's an open area of research. Very important. Does that make sense?
I had a second question. I'll let that go.
Yeah, so I guess just on that same note, are there any standards or best practices for managing models that people are using but versioning them over time, storing them, because they're effectively pieces of software, right? So like, and they can be updated, they can be versioned, but how are people storing the metadata for models?
Yes. Okay. I know that people on my team are looking at different, like, I guess you could call this like ML ops software and the pros and cons. Can anyone help me remember? There is there's some software that people are working on at Argonne to like be able to share your model with the public and be able to track the metadata. I think one person looking at this is Morley Amani. Okay, yeah. And I think like lower hanging fruit is even just remembering to save your random seeds and stuff like that. But that's definitely people are trying to figure out how we can better share our models with different versions. And I think there's probably great solutions in industry that we need to bring into research. Yes.
How do you balance your data set? I mean, do you choose the extreme cases and then a normal distribution in the middle because they are more usual, or
Okay, how do you balance your data set? I think it's dependent on the project. Sometimes we've wanted to rebalance so that we're like equally accurate across different cases, or some cases are more important. I don't think there's like a one size fits all question or answer. Sorry. Do you have any thoughts? Yeah. One approach I was looking at this summer is there's people looking at smart subset selection. So you're finding like a subset of your training data, meaning some examples from your training data that are most important. And I think some of the algorithms have the intuition that you're looking for diverse training examples, but some of them had different angles, like you want the gradient on your subset to match the gradient on the full data. Stuff like there's like a lot of people looking at that. And sorry, I can't give like a complete answer. Yeah, it's hard.
So, in solving problem questions, that fluid dynamics, the numerical methods are designed such that they conserve some properties, like energy cannot go more than what it was, something like that, like maximum principles and something like that. So that if you have two snapshots of time and you have some energy at this point, then at this point it cannot go higher than that or something like that. So if you know two snapshots, you can predict that in between two it has not gone higher than that in the numerical method. But in case of using data from the output data from the machine learning, even though you might get 2 points in the snapshots, right? But how do you ensure that it follows those principles in between?
Yeah, if you do a straightforward approach, it will not necessarily like do things like conserve energy. This is definitely a lot of papers coming out on this. I get asked to review them all the time, and it's hard. Sometimes you can put like an extra loss in an extra loss term, but that's just like a soft constraint. You're kind of encouraging it to conserve something. Some people are trying other approaches, and I don't think there's a winning answer yet, but people are working on it.